All right, students. So today we are going to be jumping into investigation number 2, and we're going to be exploring the atomic scale. You're going to need a few materials today. So go ahead and grab your interactive student notebook, notebook 1 of 2, and have that open to page 11. We'll be going through pages 11 through 13. And you're also, if you have some foil at home, going to need that as well, and some scissors. So go ahead and pause this video and go grab those materials, your notebook, page 11 through 13, some foil, just a small piece of foil is fine, and a pair of scissors. And when you have those items, go ahead and come back here and play the video again. Okay, so you might know that aluminum foil is composed of aluminum, but what is aluminum composed of? Well, let's find out. Suppose that you have a piece of aluminum and cut it in half. This is why you went to go grab that piece of aluminum. And then you cut the halves in half again. Okay? How many times do you think you could divide each half? Could we just keep doing this forever? Let's try it out right now. So get that piece of aluminum that you went to go grab and get your scissors and go ahead and cut it in half. And place one of the halves aside. Then I want you to carefully cut the remaining piece of foil in half again and place one of those halves aside as well. And I want you to do this as many times as you can. And in your notebook, record the number of cuts you were able to make with the foil. That's going to be number 1 on page 11 of your workbook. How many times were you able to cut that piece of foil in half again and again and again? If you continued cutting the foil in half, you would eventually end up with a single particle of aluminum. Scientists use the word atom to describe a single particle of a pure substance. Any substance that is composed of matter is composed of atoms. Even if you used a magnifying glass, you would not be able to see an atom. So just how small is an atom then? The scanning tunneling microscope allowed scientists to see atoms for the first time. This image was one of the first images taken with the STM. It shows silicon atoms arranged in hexagon rings. You can see those right here. So these are individual silicon atoms. And remember, hex means 6. Okay, so there's 6 of them in a ring. The average diameter of a silicon atom pictured here is 210 picometers. So if I were to take the measurement of the diameter of one atom right there, that would be 210 picometers. What is a picometer? Let's think about this. A period at the end of a sentence, like right here, in your textbook is about 300 million picometers wide. So 210 compared to 300 million is a big difference, right? So that means this atom is very, very, very tiny. Scientists use the word atomic scale to describe the size of atoms. Think about it, they're so tiny. Scientific notation is a useful way to express very large and very small numbers. Atoms are so small that you rarely deal with just a few of them. Most of the substances you interact with regularly are composed of very large quantities of atoms. So now we're going to practice writing very large and very small numbers using scientific notation. In Canvas, listed right before this presentation was the handout that said exponents and scientific notation. And you're going to need that right now in order to answer the next couple of questions in your notebook. Okay, so go ahead and access that handout. And you're going to be using that to help you answer number 2 and number 3 in your notebook on page 11. When I look at number 2, I see scientific notation is given to me. So that first number, 2.23 times 10 to the 22nd atoms. And I want to write that in standard form. Okay, so how do I do that? Remember, standard form is not using the 10 to the exponent here. It's just the whole number written out with all of the digits. Okay, so use your handout to help you write that number in standard form. And you're also going to write 1.43 times 10 to the negative 14 meters in standard form as well. Now remember, it's a negative exponent, so you're moving that decimal in the opposite direction. You're moving it to the left instead of the right. Okay. When you finish that, and if you need more time, go ahead and pause the video right now until you do finish that. But when you finish that, you'll be moving on to number 3. And now you're given the standard form. So the very large numbers with all the commas and all the digits. And you're going to use that same handout that you were using to help you in number 2 to convert these numbers that are given in standard form into scientific notation. Okay, so now you're going to be counting the places, the spaces between the digits in order to know what your exponent might be. So go ahead and pause this video and practice doing that on number 3 in your notebook. All right. Now we're going to practice matching the scientific notation form of numbers to their correct standard form of numbers, okay? So let's take a look at this. I have 9.0 times 10 to the negative 5, and I want to find the standard form of that number over here and match it. Well, I have a negative exponent, so I know that I need to move my decimal to the left by 5 spaces because it's to the negative 5. So if I moved this over to the left, I would have the width of an eyelash. You can see that that decimal that was behind the 9 was moved over to the left or shifted over to the left by 5 spaces. 1, 2, 3, 4, 5. Okay, now let's try this one. I have 4.68 times 10 to the 6. It's a positive number, so I'm going to be shifting my decimal to the right by 6 spaces. So let's go look at our numbers over here. Up, there it is. If I were to have the decimal, it's at the end right now, even though it's not invisible. If I were to go 1, 2, 3, 4, 5, 6, I would have this number right here. So this is the correct answer to number 6. Okay, we're going to do this for this number right here, 6.96 times 10 to the 8. Remember, it's a positive number, which means that I'm shifting my decimal to the right. Okay, so let's see. Do I see a number like that over here? Ah, right there, the radius of the sun. Okay, 1.8 times 10 to the 3. Got to move this over 3 spaces, so that means I should have 2 zeros at the end. 1.8 times 10 to the 3rd is the depth of the Grand Canyon. Okay, 2.2 times 10 to the negative 1. So negative number, we're shifting this over by 1 space. So it should be 0.22. There it is. Diameter of a soccer ball. Okay, now here we go. We have a very large exponent. Okay, so we're talking about something pretty large here. I want to move this decimal over 21 spaces to the right because it's positive. So do I see a number? Right here. Look at all those spaces, all those zeros. Okay. Now we're doing the exact opposite. This is a very tiny, tiny number, 1.6 times 10 to the negative 35. That means I need to shift this decimal to the left by 35 spaces. See how tiny this number is? Okay. And now I have 1.6 times 10 to the 0. anything to the 0 power is 1, so it's just 1.6 times 1. So it's still just 1.6. And you'll want to make sure to check your answers after you do this. On the next 2 slides, you're given more practice of matching the correct scientific notation with the standard forms of those numbers. Go ahead and do these 2 slides on your own and check your answers for the extra practice of converting those numbers between scientific notation and standard form. All right, now I'm going to assign you either length, volume, or mass, okay? And you're gonna write that down in your notebook. This is at the top of page 12 in your notebook. So how I'm going to do this, if you were born between January and April, so that means January, February, March, or April, you're gonna be working with length. If you were born in May, June, July, or August, you're gonna be working with volume. If you were born in September, October, November, or December, then you are going to be working with mass. Okay, so write down whichever unit you're going to be using. That's number 4 on page 12. And now I want you to choose 5 different objects around you and sort them by size based off the category that I just gave you. Okay? Go ahead and pause this video. Go find 5 items around your house or around you right now, wherever you're at, that either have to do with length, volume, or mass, depending on when your birthday is, and sort them based off of your category. All right, let's wrap up what we just learned today. So, why do scientists and engineers use scientific notation to describe objects on the atomic scale? Why do we do this? Why do we care about scientific notation? Well, scientific notation helps express quantities of things that are very, very big or very small to describe. The size of an atom is so small that it's easier to describe it using scientific notation. The number of atoms in something is so big that it's easier to describe using scientific notation. How can scientific notation help scientists organize objects by size or magnitude? Well, the exponents used during scientific notation help you to easily distinguish between different scales of objects. So if you remember when we were doing the practice matching a few slides back, if it had a negative exponent, a large negative exponent, like 10 to the negative 35, we automatically knew that was a really tiny number. On the other hand, if it had a large positive exponent, like 10 to the 21, then we knew it was a very large item or object that we were talking about. What are some quantities that might be better expressed in scientific notation? Possible examples that might come to mind would be the number of stars in the Milky Way galaxy, the number of atoms in 1 gram of a substance of something, or even the wavelength of a light wave. All right, guys, so the takeaway from this video, we want to feel comfortable taking a number and converting it from standard form to scientific notation, and we also want to realize that scientific notation is really helpful for understanding that the items that we're talking about, or the distances, or whatever it is that we're talking about, are very large numbers or if they're very small numbers. And we can easily do that using scientific notation.